Chapter 2, Section 5, Reasoning in Algebra and Geometry. So we're going to begin with some properties. We've talked about some of these in the past, but we're just going to review. So the reflexive property. A quantity is congruent or equal to itself. So a general example would just be A equals A. If we're talking about, let's say, a line segment, we could say AB is equal to itself. The symmetric property says if A equals B, then B equals A. So in other words, if XY equals TV, that means that that's the same thing as saying TV is equal to XY. The transitive property says if A equals B and B equals C, then A equals C. So if we're talking about a problem and it tells you that AB equals BC and BC equals CD, that then implies that AB equals CD. The addition postulate we've talked about in the past, like the segment addition. If equal quantities are added to equal quantities, then the sums are equal. So let's think of this in a slightly different way. Let's think of it as if XY equals RS and AB obviously equals itself. Well, these are equal quantities. If we add AB to both sides of this equation, they'll still be equal. So XY plus AB will still be equal to RS plus AB. We added the same length to both sides. The same thing goes for the subtraction postulate. If we're talking about the same example, XY equals RS and AB equals itself, we can say that XY minus AB is still equal to RS minus AB. Multiplication postulate, again, same thing. We know that 2 equals itself by the reflexive property. So if we say that RS equals TV, we can say that 2RS will still equal 2TV. So if equal quantities are multiplied by equal quantities, the products are equal. Also doubles, which is what we just showed. Division postulate states that if equal quantities are divided by equal non-zero quantities, then the quotients are equal. So we'll use 2 equals 2 again, and we'll use RS equals TV again. That means that this works for halves as well. RS divided by 2 is equal to TV divided by 2, which you can also write as half of RS is equal to half of TV. That could be said to be using the multiplication postulate as well. Finally, we have the substitution postulate. So this states that a quantity may be substituted for its equal in any expression. So let's say I give you that AB equals BC, and I give you AB plus BC equals AC. Well, you could substitute in BC for AB and rewrite it as BC plus BC equals AC, which would mean that 2BC equals AC, and you could solve whatever question was being asked from there. So you use deductive reasoning when you solve an equation. You can justify each step with a postulate, a property, or a definition. This is very important. You can use a postulate, a property, or a definition. If we've covered it, then you can use it. For example, you can use the distributive property to justify combining like terms. That's important. If you think of the distributive property as AB plus AC, which is the same thing as A times AB plus BC, or AB plus AC is the same thing as B plus C times A, that means that 2x plus x is the same thing as 2 plus 1 times x, which would give you 3x. So whenever you're combining like terms, it's important to know your justification would most likely be the distributive property. So let's look at this example. We're asked to find the value of x and to justify each step. They tell us that AB bisects angle RAN. So we did this in class. If it bisects it, that means that these two angles are congruent because it's bisecting the whole, which means that x equals 2x minus 75. But let's write all of this out so we have a game plan. We'll write all of this out and we'll justify each step. So just as we said, our first step is going to be to set x equal to 2x minus 75. And the reasoning behind that would just be an angle bisector cuts an angle into two, and we're going to say equal angles because we're setting them equal to each other. The next step that we would do would be to add 75 to both sides. By adding 75 to both sides, it looks something like this. We don't have to write this out, but just to understand where it's coming from. You're adding the same number to both sides to get that x plus 75 equals 2x. And because that's what you're doing, because you're adding 75 to both sides, you would state that you're using the addition property of equality. Then we would have to subtract x to the other side. So we'd get 75 equals 2x minus x, which is the subtraction property of equality. And finally, like we said up here, we're combining like terms. So this is like thinking of it as 2x plus x is 2 times 1 plus x. But instead it's 2 minus 1 times x. So here we finally get 75 equals x, and that's by the distributive property. And that's the end of the proof. You can now say that x is 75 degrees. Now this is a proof. You just did your first proof. If we were to write it as a 2-column proof, this would be our statement. This would be our reason. And we would just draw it as a table. And that's a proof. This is the symbol for the end of the proof. You've completed your proof. So here we have again our reflexive, symmetric, and transitive property. So if line segment AB is congruent to line segment AB, or angle A is congruent to angle A. Like I said, usually angles are labeled with 3 points, but sometimes the textbook or Regents questions label it as 1 point. You should still label it as 3 points. Symmetric property says that you can reverse them, so A is congruent to B, B is congruent to A. And transitive property says if these two are congruent and these two are congruent, then the first and the last are congruent to each other. So we're going to write a 2-column proof. In order to do that, we need a statements and a reasons column. Now it tells us the given statement is that AB is congruent to CD, which we can see is already marked off in the picture. So we want a game plan to figure out, to prove that AC is congruent to BD. Well, we know that AB is congruent to CD, and using the reflexive property, we can show that BC is congruent to itself. This is how you show that it's congruent to itself. Basically put an X through it. Well, if we use an addition postulate, we can show that AB is congruent to CD and BC is congruent to itself, which means that AB plus BC must be congruent to CD plus BC. So now we have our game plan. Now we're going to write our proof. So we're going to start by just first stating the given statement. Line segment AB is congruent to line segment CD, and the reasoning is just that it was given. Now we're talking about using addition. We're talking about making two things equal to each other, so we can't leave it as congruent. We need to change it to AB equals CD, because that is true, and our reasoning is that if two line segments are congruent, then their measures are equal. So now we can go on to state that BC is equal to itself by the reflexive property. Which means that we can add BC to both sides of this equation, so plus BC and plus BC, and that gives us AB plus BC equals CD plus BC, and that's by the addition property of equality. Now is where it gets a little bit tricky. So we want to show that AC equals BD. Well, by looking at the picture, we can see that AB plus BC gives us AC. Well, this is the line segment addition postulate, which we were talking about in the previous chapter and is coming up again now. So AB plus BC equals AC. And you can say the same thing about CD plus BC, how that equals BD. So this is by the segment addition postulate. Well, now, by using substitution, I can show that since AB plus BC equals AC, and since CD plus BC equals BD, we're going to plug that in here, we can state that AC equals BD by the substitution postulate. Finally, we can switch it to congruency, so line segment AC is congruent to line segment BD, and the reasoning behind this is just that if two segments have equal measures or equal lengths, they are congruent. And now we've finished our proof. So you can put your little box in the corner to show that it's completed.